All right, so this is the third of our videos about ethics. This one is going to focus on the limits of p-values and the worry about multiple comparisons and what people call p-hacking. So one problem we have when we do traditional statistics in a data science setting is that almost every formula we have, if you think of your favorite stats formula, maybe the T formula, right? The confidence bound has this formula that's like S over square root of N. And so the sample size is an important part of our confidence and an important part of our precision in our estimates. So if our N's are getting super duper big, right, in the realm of 10 million or even hundreds of thousands, that square root of N is going to be big. Anything we divide by that number is going to be very small. What that means is that when we're doing big data analysis, almost everything is going to be significant in a p-value sense of the word. Now, that's not to say that everything's going to be important. And an idea that came up when you were talking about statistics in your intro stat course, the idea of practical significance. So instead of thinking about how significant it is, because really all we care about is it's significant or not, having a p-value that's teeny tiny isn't actually more useful than having a p-value that's just interesting enough that we think that the results aren't due to chance. So instead, we talk about the idea of effect size. And there are several measures of effect size. Some of them we're going to talk about. More complicated ones like R squared or Cohen's d are calculations you make to think about how important or how useful these differences are. But a very simple measure of effect size is you just subtract the one number from the other and see how big it is. So for instance, you've seen commercials for different weight loss programs, and here's a whole bunch of different diets, and some are more expensive, some are less expensive. Some, like Weight Watchers, you pay them a fee for them to help you lose weight. Nutrisystem's another one. You have Marie Osmond or Dan Marino or whoever telling you on TV how that program helped them lose weight. And sometimes they'll even say that some of them were shown to be better than dieting alone. But what happens when you go in and look at that is that the difference between most of the various systems is about 3 pounds or 4 pounds. So that's not to say that's not something, but you probably don't want to pay hundreds of dollars to join a program like Weight Watchers if your average weight loss is going to be 3 or 4 pounds. What complicates it is that the standard deviation is pretty big. So some people don't lose any weight at all. Some people actually gain weight on those programs. And especially if you look at the long-term effectiveness, what most research shows is that the modest long-term weight loss has very little to do with what plan you choose, and instead it has to do with you being willing to stick with it and to make long-term life changes as opposed to doing short-term diets. Now, some of those systems like Weight Watchers or Nutrisystem, part of their appeal, and one reason why I think they do work for many people, is because they show you how to become that person who eats less on a regular basis rather than simply helping you diet in the short term. So this idea of effect size is going to be pretty important. And this idea about p-values, I think, is going to become less important. And as big data becomes important and as statistics moves forward, there's actually an issue of the American Statistician, which said we need to move beyond using p-values as kind of this magic yes-no idea. And in particular, the idea that there's a 0.05 line, and anytime the p-value is less than 0.05, it's interesting, and anytime it's not, it isn't. That's something that I think is going to be falling away as we move forward into the future. And so, one reason for that is this thing about this sample size that I talked about. You're going to divide by the square root of n, and your p-value is going to be tiny for pretty much anything that you do. The other thing going on is that there could be confounding variables that you didn't measure in your data science. Again, we use existing data that was collected by other people a lot of the time. And so you can wonder about confounding variables, but you can't really show that they're going to be important. One last problem we have is the problem of multiple comparisons. And multiple comparisons is the idea that if you compare a whole bunch of things, the odds that one of them is going to be significant is going to come up. So there's an XKCD cartoon. I don't know if you know XKCD, but the first panel says jelly beans cause acne, and so they investigate and they don't find any link, the p-value is greater than 0.05. But then the rumor is that a certain color causes it. So now they start and they look at each color independently of each other. And what you can see is these studies, each one doesn't find a significant one except for this green one. And not by accident, they did 20 panels here of 20 different colors, all the way from red and blue down to weirder colors like lilac and turquoise and beige. And what they found was that one of those colors of jelly beans really was significant. But because that was part of this multiple comparison, if you're wrong 5% of the time, that's 1 in 20, you would expect that 20 experiments would give you one of those outcomes due to chance alone. And of course, the final panel is that the green jelly beans are linked to acne. Instead, we should think about significance more excuse me, as a thing that makes us investigate further. That after you do the 20, then you would want to replicate the study with new data before you got too excited about the change. If you played a game like Yahtzee, where you roll 5 dice, you'd know that it's actually pretty rare to roll 5 dice and get all 5 of them to come up on the same number. That's called a Yahtzee in the game, and it's cool, and you get lots of points. And to do that once is actually pretty rare. But in the game of Yahtzee, not only do you roll a whole bunch of times, but you get to pick which dice you re-roll, which increases your chances. And in fact, most of the time in a game of Yahtzee, you do get a Yahtzee. At least one of the players does. And so this idea that you can go from a low probability event to a high probability event through repetition is there. I'm thinking about things like drunk driving, right? We know that drunk drivers have a higher risk of accidents, but it still doesn't get to the point where a single time drunk driving leads you to a very high % of an accident. And in some ways that's worse because you do it the first time and you're fine and you feel like you can do it again. But if you do it 50 or 100 times, the chances that you will be involved in an accident or that you'll be pulled over by a policeman start to grow and grow and grow. Okay, so my last example is about HIV tests. And as you know, HIV is a sexually transmitted disease. And one of the things about it is you can have it for about 10 years before it starts to show any effects. In some cases it does show symptoms much quicker. But once it starts, it's actually harder to reverse. So this idea that you want to find HIV much sooner is important, which is why HIV tests are very common. Now, there are 2 medical tests for HIV. One of them costs about $1 to run, and the other one costs about $100 to run. Now, that's not the cost to you, that's the cost to the doctor, to the insurance company for the kit. You would still have to have the costs of the people doing the test. But you can imagine that the test that costs $1 is the test that you typically have whenever somebody has, free AIDS testing or something. You have that first test. And that $1 test is good in the sense that it has a very low error in the sense of if it says that you don't have HIV, you almost certainly do not, with the asterisk that it takes a little bit of time. So you have not had AIDS or HIV for more than a month. And that's pretty certain from the $1 test. But if it gives you a positive result, it doesn't mean that you have HIV. And in fact, its false positive rate is actually fairly high. And depending on the underlying prevalence of AIDS in that area, in some cases, more than 3/4 of the results are false positives. And in some cases where AIDS is rare, the false positive rate is over 90%. So if you get that first test, the doctor or the nurse doesn't call you and say, oh, you tested positive, but we're not sure. Instead, what they say is, come in and we're going to run another follow-up test. That follow-up test costs about $100, which again, doing that for free with lots and lots of people is maybe expensive to do. But anyone who tests positive, we would then go ahead and run this fancier test on, and that would give you the accurate result that would tell you. And sometimes just running the test more than once would do that. So this idea that significance by itself isn't really important, but it identifies that you need to investigate further, you need to do a second follow-up, you need to go in more detail and do that. All right, so at the end of this video, I'm going to link you to another video by John Oliver. It's from HBO's his Last Week Tonight show. And he talks about p-hacking in more detail. I will warn you, it does have some strong language. It is HBO, so I apologize in advance for that. But I think it really does a good job of getting to this idea about p-hacking and why, in a very practical public sense, p-hacking is a problem.